Alright, so we were talking about applications of Cayley's formula. So, in order to talk about Cayley's formula, you need to know what is a tree and what is a graph. So, you've probably gone over in your discrete math class. So, a graph is just a finite set of the vertices and relationships between the pairs of vertices. They're called edges. While a tree is a graph with no cycles. Cycles being the path where it goes from the starting vertice to the ending vertice, only repeating those vertices. So as you can see on the left down here, this is a 4 vertice graph. So it has all its vertices, edges connecting the two of them. While over here we have a 6 vertice tree. So if I were to go from 6 here on a path to 1, that works, but I cannot go from 6 back to a path to 6 without having to double up on the vertices. So what is Cayley's formula? It's author Cayley over here on the left. So the idea is for Cayley's formula that when you have a distinct amount of vertices, we're going to call them n in this scenario, that your number of trees that you can make are n to the n minus 2 power. So as you can see kind of here on this example, when I have 2, you take 2 to the power of 2 minus 2, which is 0, you can only have 1. If I take 3, it's 3 to the 3 minus 2, which is 1, so 3 to the 1, 3. 4 gives you 4 to the 4 minus 2, which would be 16, as you can see all the different ways that they have them down here. So just as a little practice problem here, so given the 9 mercenaries from TF2, how many distinct trees can you make? So this is a pretty simple, straightforward problem. Given 9, you can plug that in, 9 to the 9 minus 2, which is 7, 9 to the 7th, which is 4.8 million approximately. That's a lot of trees. So when we talk about Cayley's formula, we also talk about this guy, proof or sequence. The idea is that on a tree, you take the vertice with the lowest degree and you record the vertice that's connected to it. So in this example for this tree that we have down here, so the vertice here is, with one of the lowest degrees, is 1. I'll start up here. So I record down 4. This is the first vertice in my sequence. So then I can take 2, which also has a degree of 1. I could write down 4 again. Now I remove that. Take 3, remove it, write down 4, and then take 6 over here, remove it, 5. So we know the length of the sequence is n minus 2, and being the number of vertices. So we have a sequence of 4, as you can see up here. We also know that there is n to the n minus 2 number of sequences for a given n. There's a whole proof about this. It's a little bit outside, I think, my scope, most of our scopes here, except maybe my discrete math professor. Maybe it's outside his scope. I don't know. I'll have to ask him. But the idea is here, you can, my mouse is going nuts here. A tree could be rebuilt from the sequence such that it has n minus 2 length and n to the n minus 2 sequences. So walking backwards, I can rebuild this tree. It won't be exactly the same, but I can still rebuild it into another tree. So we also have, Cayley had a formula for a forest. So a forest with n vertices is a graph that contains no cycles, but does not need to be connected like trees. So these here, my mouse is going away again, this is a forest. You have 2 trees, and if I start here, there's no way I can get back to it again, no matter what. But they're not connected to each other. So they both exist. They're both graphs. They're both even trees. But they're not connected to form a full graph. And there's still no cycle. So we have this formula here. T n to the k. In this case, k is the number of trees that we have, while n is the number of vertices of the trees. So in this case, k times n to the n minus k minus 1. If you were to plug in 1, assuming you have only one tree, you will notice it simplifies down to n to the n minus 2. Fun fact, a little bit about this, Cayley never actually proved this. He sort of just said this exists and this works, and no one really questioned it So they just kind of accepted it for a while, and then it was proven at a later time. You can look up. There's a lot of interesting ways how that proof works. The binomial theorem is used in it. Once again, a little bit outside my knowledge field and probably most knowledge fields as we're doing this. So now we have how many labeled force would there be if the Team Fortress 2 Team Fortress 2 mercenaries from red and blue team, with each team having 9 mercenaries still. So now you have 2 trees, red and blue, each with their 9 mercenaries. So you plug in, so our K is 2, our N is 9, which would mean 9 minus 2 minus 1, which gives us 6. 2 times 9 to the 6 gives us another very large number. Over 1 million? Yeah. There we go. So given the sequence, this tree was deconstructed and gave us sequence 1, 1, 5, 5, 4. Recreate the tree. So what do we know? We know that the sequence is n minus 2, with n being the vertices. So we have a sequence here of 5. So we know that this tree has to have 7 vertices. We also know 1 has a degree of 2 at least, 5 has a degree of 2 at least, and 4 has as well a degree of 2, because they all were able to exist. They have to have a degree greater than 1 in order to still be a part of the sequence. So the little animation error there. So in this case, we got 1 and 1, and we got 5 and 5, and then for our 4 here we can hit 7. But that didn't give us quite enough edges to actually make our tree. So we just throw in this one little connecting edge here, and it still works okay. This might not have been how the original tree was, but it's still a tree that fulfills our proof or sequence. Alright, so given the number of distinct trees is 16, how many vertices are there? This one's a little bit trickier. Some people will have a, I'm sure, long mathematical way of solving this, but if you just remember, it's n to the n minus 2, and if you remember in the beginning, there was one of the trees that did have 16. In this case, it was the one with 4 vertices. So 4 to the 4 minus 2 gives you 16. Now, let's actually try to apply the stuff we've learned in an actual scenario to prove that Cayley's formula has a use outside of just discrete math here in our graph theory. So you're working at this little fast food restaurant. We're going to call it ABC Fast Food. So they want to start using their self-ordering stations to take orders. Much more efficient, easier to get orders mass-produced. So they tell you that there's going to be this main order menu, and from there you should be able to choose either a burger, fries, or a drink. If they choose a burger, we want to know if they want to make it a combo. If they choose fries or a drink, we want to know what size it should be. So now we got to make a tree. So if you're a computer science person, this could very well be something asked of you. So you got to think, well, first we have our main menu all the way at the top here. It's going to be our very base thing, which has to have the 3 options of burger, fries, and a drink. And from those, we need to present the options for burger if it has a combo, or if they don't want a combo. For fries and drink, we need small, medium, large, and small, medium, large. Then we have to assign our little paths here. So you can see, we've made a tree. I bet you didn't expect that. All right, now how many ways are there to make the tree? And then we're going to create a proof or sequence for the tree. So there's 12 vertices. We do 12 minus 2 is 10, which is, well, you can read the number on the screen. I'm not going to try to create the words for explaining that monstrosity of a number right there. So a sequence, for example, we take burger and burger, and then fries, 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 drink, 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 main menu, main menu, main menu. That breaks it all the way down, back down to the main menu for us. So use the previous sequence, create a tree. So we've got burger, fries, and drink, and we have our main menu. So from there, burger needed 3. Well, burger needed 2. Sorry. Combo, no combo. Small, medium, large. Now, this is exactly where sometimes application doesn't work quite in the same sense. In theory, you would have created small here and medium here, large, combo, large, medium, no combo, medium. You could have created a few different scenarios, but it wouldn't be quite the way that it was asked. So when there's that previous number of the 6 billion or however large it was trees, that's not following the structure that is presented here. I mean, there's only so many ways you can make that tree. There's really only one. This is just pretty much the same tree, but just remade. But like I said, I can take stuff like the small here, put it here, switch those two out, that's still technically accurate in the proofer sequence, but it's not accurate as to what our higher up might have wanted. You'll have a very bad menu if there's asking for a burger and it says small or no combo. Your user base might be very confused. Let's see. So if a company decides it wants 3 of these self-service machines, how many labeled forests would there be? So this is we have 3 self-service station trees, and we want to know how many different forests could exist with that. Which is, again, another obscenely large number that 1.3 trillion, which is a lot. Sure, any computer you would set that up for would be there a while doing the calculations of drawing all those trees. So just a little bit of source here. I think that's it. So I hope you learned something, at least learned something from this, trying to make it a little bit more enjoyable.